I don't know if I did the syllabus in here yet. I think other than the syllabus, which I probably needed to double check on, I think Canvas is set up, but I'll hopefully have all that fixed in the next day or so. But I'm just, anyway, I'm trying not to forget things. If something seems out of place in here, just send me an email, let me know, all right? Because every so often things get left over from the previous course copy, and I don't delete them, and then students are like, well, assignment due tomorrow or something. I'm like, wait, what? No, you know. So anyway, I'll begin with a word of prayer. Dear Father, we thank you for this day, and I thank you for this class. I just ask you, bless our work today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me reiterate the general setup here, guys, which is this. So we're going to talk about the Gauss-Jordan elimination method. And so before I even do that, I'm just going to state the definition for a system again. So let x1, x2, all the way out to xn be variables. And suppose a, I, j, and b sub I are in the reals for 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. Then we have a11 x1 plus a12 x2 plus dot 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 plus a1n xn equals to b1. That's my first equation. And then my second equation, a21 x1 plus a22 x2 plus a2n xn equals to b2. There's my second equation. And this goes on. We have m total equations, m as in mommy, n here as in nanu nanu. So here a, m2, a, m, n, xn equals to bm. So what I've written down here is a system. Let me call this all together star. So star is a system of m linear equations in n unknowns. All right. Now, if there exists b sub I not equal to 0 for some I, then star is non-homogeneous. If bi is equal to 0 for all I, then star is homogeneous. All right? So that's the terminology here. The solution set. What is the solution set? The solution set basically is just this. It's x in Rn such that you know, x equals to x1, x2, xn solves star. All right. So this is the solution set. It's the set of all x in Rn which simultaneously solve all m equations at once. All right. So a little bit more notation. So definition. The augmented coefficient matrix for star is A with B slapped onto it, where by this I mean AB is equal to, so you got like A11, A12, all the way out to A1n, and then B1, A21, A22, A2n, B2. And so it's the same pattern I had written in the other spot there, guys. It's just now what's the difference here? So the augmented, yeah.
Well, we're just assuming that each variable in the matrix on the left of the furthermost right column has an unknown variable attached to it, so we can just use numbers
Mm-hmm. So we're using numbers instead of
a system of equations.
Instead of system of equations, right? There's no, I mean, so what you're telling me, I think, is that there's no x's over there, right? So the x's are variables, but since x's are just labels for the unknowns, if we don't refer to them explicitly, if I give you this box of numbers here, right, and we agree that the variables in question are x1 through xn, you can write down from this that, right? So there's a one-to-one correspondence between this kind of system of equations and this box of numbers, right? So we can keep track of the system of equations with the box of numbers and vice versa, provided we understand the context, right? We have to have a settled idea about what the variables are in order to make sense of this. Let me give you an example of that idea before I lose too many of you. So like, just for a specific example of what I'm talking about, I can have, you know, x1 equals to x, x2 equals to y, x3 equals to z, you know, and I can have something like x plus y minus z equals to 7, and 2x plus 8z equals to 23, right? That's a system of two equations and two unknowns. The augmented coefficient matrix for this would be what? What do I put in the one spot I haven't filled out yet here? What do I put here? 0. He says 0. Why do I put a 0 there?
Because there's no 0 y's.
There's 0 y's, right? So, oh man, well, I'm going to have to squeeze it in here, guys, but this, I guess I could do it over here. So this is, quote unquote, A, and this is, quote unquote, B, all right? So B is what we call a column vector, right? The column vector of inhomogeneous terms, right? Sometimes I'll just refer to B collectively as the inhomogeneous term, but understand it's the collection of like all of them together at once as a vector there. A is a matrix, right? A is called the coefficient matrix. It has all the numbers that formulate the system, right? The coefficient matrix. Now, and what size is this matrix? It's an m by n. That means m rows, n columns. All right, so I'm just trying to settle some terminology with you guys. All right. So we looked at how to solve some very particular examples last time, right? But we need to kind of like formalize that a little bit and point out that there are, okay, so the next definition I would say, well, hi to you as well. It's random. So definition, star and star star are equivalent systems if they have the same solution set. right? So what I'm talking about with star star, I haven't even written it down, but like imagine you take what I wrote right over here at star and put like a tilde over every one of these coefficient matrices, or put a, replace A with something else, all right? Some other letter. So you have possibly different numbers everywhere. And yet, they have the same solution set. That would be an equivalent solution, equivalent system. So like, just to give you an example of what I mean by star and star star, let me just do that here. If this is star, an equivalent system, I'll put it in red, could be this. 2x plus 2y minus 2z equals to 14, and 2x plus 8z equals to 23, right? This would be star 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 and star star. In this example, would be equivalent systems. Do you understand why? If I multiply one of the equations by a non-zero constant, does that change which x, y, z makes it true? Certainly not, right? So that's it. So star star there is an equivalent system. So my claim to you is that there are 3 natural things we can do to the augmented coefficient matrix which will give us an equivalent system. These are the elementary row operations. So what I'm trying to describe right now is things we can do to the augmented coefficient matrix which will not change the solution set. All right? So the things we can do, one of them I already pointed out. I think we've done pretty much all of these last time. First of all, we can take rho I and we can replace it with c times rho I. We can, so for c not equal to 0. And this is called row rescaling. We can rescale a row. Number 2, we can take rho I and we can replace it with rho I plus rho j. Right? This is row addition. What does that logically correspond to that we did last class? Do you guys remember? Remember last time we talked about solving equations, and we talked about we could add equations as a method of solving, right? Or we could substitute, was the other thing you guys told me. We could do substitution, but I prefer the addition typically. Not always, though. We did the back substitution at the end of class, right? That wasn't row addition, that was something else. But if you think about it logically, if I was to take this, the original system star, and if I was to add 2 equations, right? If I was to add the the jth row to the ith row, that would give me a new equation, right? And in the new matrix that corresponds to that system, that would replace rho I with rho I plus rho j. So this is what happens at the level of the matrix if we were to add equations, is the idea. The other one that we can do, and this is just kind of weird, but it actually matters, is we can take rho I and we can put it to rho j. Let me just say it this way. We can flippity flop these. We can do row swap. Row swap. These are the elementary row operations. And what I'm going to show you is that we can use elementary row operations to change the system that we're given to a very simple system, which is stupidly easy to write down the solution from. All right? So I'm going to illustrate by example. And once I've done a few examples, then I'll tell you what the general algorithm is, okay? So my first example is relatively simple. So example 1. Here we have x1 plus x2 plus x3 plus 2x4 equals to 10. And I have 2x1 plus 4x2 plus 6x3 minus 10x4 is equal to 0. All right. So, so my first order of business here is to write down the corresponding augmented coefficient matrix. So I take this, and this gives me 1, 1, 1, 2, 2, 4, 6, minus 10. Oh, sorry, I forgot the last. I usually put a bar here, you know. That bar is just organizational, yeah? So that's my augmented coefficient matrix, all right? Okay, so then what? So what I'm going to do is do some simple row operations to show you how we can, you know, do things here. So first of all, I want to get rid of that 2. So what I'm going to do is I'm going to do row 2 minus 2 row 1. All right, row 2 minus 2 row 1. So I've got 1. So row 1 is not changing at all. All right, so what's row 2 minus 2 row 1? So I take 2 minus 2 times 1 is 2, so I get 0 here. 4 minus 2 times 1, which is 4 minus 2, which is 2. 6 minus 2 is 4. And minus 10 minus 2 times 2 is minus 14. 0 minus 2 times 10 is minus 20. All right. That's funny. I did it a different way in my notes. These are not the notes this is just a set of handwritten notes I have. I'll try to post the PDF of this for you guys if it helps you. But I'm writing everything down on the board so you're not missing anything. All right, so next up, to make things simpler, so like, all right, next thing I'm going to do is, I want to get rid of, my goal is to make this go away. I want that to go away. But to make things easier, my next thing I'm going to do is I'm going to take row 2 and I'm going to divide by 2. All right, so I have 1, 1, 1, 2, 10 for my first row. And my second row, I just divided by 2. So I've got 0, 1, 2, minus 7, minus 10. All right. So I did the row rescaling. Then what? Well, how would I get rid of, so you guys tell me, if I want to make this 1 become a 0, what should I do? Subtract, right? So the way that looks here in my notation is row 1 minus row 2. All right, so that gives me, row 2 doesn't change, so I have 0, 1, 2, minus 7, minus 10 down here. Row 1 becomes, notice that when I subtract row 2 from row 1, you notice this 0 here? Super nice, that means nothing happens to that 1. All right, there's a strategy here that I'll explain as we do a few more examples to get it under our belt. But so nothing happens with the first column, stays the same. That 1 becomes a 0. 1 minus 2 is what? Minus 1, right? And then 2 minus a minus 7 is also known as 9. And 10 minus a minus 10 is 20. All right. So before I say anything more, let me comment on the notation that we're using. The row operations, the notation I'm using is simply this. whichever row comes first over the arrow is the one I'm modifying. See that? So like, I'm changing row 2, I'm changing row 2, I'm changing row 1. Right? When I described it over here, I used these arrows, like row, So what I'm trying to say is, essentially a shorthand, like, for instance, this one here, you can think of, I would have said, like, row 1 goes to row 1 minus row 2 in this kind of notation, right? But we're going to get really tired of writing that between all these matrices, right? So it's nice to have a quicker way to say it. And our convention is simply whichever row comes first is the one we're modifying. And I also, in as much as I remember, well, I mean, this is, and I also try to draw the arrow on the row that I'm actually changing. That also helps the reader understand what I'm doing, right? So that's the notation. Okay, so then what? So at this point, we're done. This right here is the so-called reduced row echelon form of AB. So this is reduced row echelon form. There is a theorem that I won't prove because it's totally boring to prove, but there's a theorem which says that there is a unique reduced row echelon form corresponding to any matrix. And that if you do these elementary row operations, right, it doesn't really matter what order you do them in, but if you do them, and you get to the reduced row echelon form, that is a unique ending point. So we can all take different journeys. We could, like, some of us could multiply by 2, some of us could add a half of the other row rather than doing that. Like, you could do different steps. But at the end, if we're to the reduced row echelon form, that is unique. Now, what makes the reduced row echelon form the reduced row echelon form is that as you read the matrix from left to right, the leading non-zero entry in each row is 1. All right? And if you're in a lower row, if your leading entry is 1, there has to be zeros above it. All right? Now what happens after the leading entries, whatever. But, so let me just try to describe the reduced row echelon form. So, reduced row echelon form of A has 1 leading entries of 1 in each non-zero row. And number 2, if the row is not at the top, all the entries above a leading one are 0. So this particular matrix is kind of silly in the sense that there's only 2 rows to think about, right? So there's not much to say here. Let me give you another example. Actually, okay, fine. One more example about that. Then we'll circle back to what the matrix means, all right? But, so this is just to further expand on what I mean by rref. Example 2, if I had, for example, the matrix 1, 0, 1, 0, 1, 3, 0, 0, 1, 0, 0, 0, 4, 5, 6. All right, so if this is, I'm just going to give this, let me call this matrix M. All right. That matrix M, it's already in its reduced row echelon form. This one's already in the reduced row echelon form. Okay? Like, it's helpful for us to have some sort of more concise terminology about what I mean by all this, because, well, it'll just help you ask questions you're going to ask as we go on here. As soon as you understand what's going on, there are questions you're going to ask, and having this language is going to make it easier for you to ask. So, in other words, this is already equal to rref of M. All right? If I asked you to do the Gauss-Jordan elimination to find the reduced row echelon form of this matrix, you should be like, okay, write it down, I'm done. You know? So, this right here is what's called E1. This right here is what I call E2. This right here is called E3. So these are the so-called pivot columns. Although that's kind of a perverse choice of terminology here because I didn't do anything. If you go back and look at my example 1, pivot columns were columns 1 and 2. The reason they're called pivot columns is you're sort of pivoting around the leading one to try to sweep everything out below it that's non-zero. So I like, like my third step back over here, my pivot position, my first pivot position was the upper left top corner of the matrix, and I subtracted row 1, I subtract words. I did it back here. So I subtracted twice row 1 from row 2 to get rid of the non-zero thing below the leading one. That's pivoting. And then I was pivoting on this position next. I pivot on this position to sweep out the one above it. Okay, anyway, something like that. So the pivot columns are the non-zero, the columns which are just E1, E2, or E3. And the other two columns are what we call non-pivot columns. So these two guys, non-pivotal columns. All right. Let me give you a definition of the EI that's a little bit more concise. So like, if we calculate EI and we calculate the jth component of that, it's what? It's 1 if I is equal to j, and it's 0 if I is not equal to j. So these things here, E1, E2, all the way out to En, is known as the standard basis for Rn. So another way I can say what I was saying in this comment over here is simply to say that if we've done our job correctly, the reduced row echelon form of the matrix will have pivot columns where every pivot column is a standard basis element. All right? Yeah. Here's the first one. Here's the second one. And here's the third one. So in R4, it has standard basis E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is, that's a great question. So thank you for that. Because this is a logical definition, but you don't maybe get that yet, and that's cool. It also gives me a chance to talk about my perverse row column notation. So this here, understand, is a shorthand for this guy. This is a shorthand for this one. And this is a shorthand for that. And this is a shorthand for this. Watch what I'm doing here. This is a little bit subtle. E1 is not equal to square bracket 1, 0, 0, 0. This is a row vector. This is a column vector. They don't have the same size. All right? For two matrices to be equal, they have to have the same size. So we can't have a row vector is equal to a column vector unless they're both like 1 vectors, which is kind of a perverse case, you know, the 1 by 1 case. But okay, anyway, so does that make sense? What you asked me what the standard basis is. So there's still something that's a little bit left out here, describing what the rref is. It has to have leading entries of 1 with non-zero row. For each non-zero row, there have to be zeros above each leading one. But the other thing is, we have to have all of the 0 rows at the bottom of the matrix. Every 0 row is at the bottom. Right? All 0 rows at bases. So like, you see there's a 0 row here? It's at the end of the matrix. All right. So now that I've spent 10 minutes trying to describe a little bit about like what are we after in terms of reduced echelon form, now let me return to the question. So first of all, one thing I should say is like echelon. What does that even mean? Anybody know?
Section?
No.
Echelon is like a rank, right?
Like a rank, right? But it actually is from like the word for like stairs. So it really legitimately means that it's like a reduced stair step form. You could think of it that way. Reduced stair step form. See, it's like a stair. If you just erase the zeros, you know, maybe you can see it better. I don't know. Kind of like a stair. So, what advantage does this give us? Like, how does this help us with the original system of equations? So every one of these steps that we did for my example 1 didn't change the solution set, right? But now that we've got to the final step right here, notice that this gives us x1 minus x3 plus 9x4 equals to 20, and x2 plus 2x3 minus 7x4 equals to minus 10. You might say, well, how is that better than the original equation? Well, it's a little bit better. So I can solve for x1 as x3 minus 9x4 plus 20, and I can solve for x2 is equal to minus 2x3 plus 7x4 minus 10. And I can take those and I can write my solution set. And my solution set here has the form x3 minus 9x4 plus 20, comma, minus 2x3 plus 7x4 minus 10, right? What's x3 equal to? It's x3. What's x4 equal to? Well, it's x4. Such that x3 and x4 are real numbers. And this, my friends, is the standard form of the solution set to the system that I wrote in example 1 here today. That is the standard form of the solution set. Let me put it into words. The standard form of the solution set is formed by calculating the reduced row echelon form of the matrix, the augmented coefficient matrix, and then writing the pivotal, you write the pivotal variables in terms of the non-pivotal variables. In other words, the non-pivotal variables serve as parameters for the solution set. Let me write that down. Non-pivot variables serve as parameters for a solution set. Yep.
When you're doing your row operations, can you choose which pivot variables you want, or are there only however many options that are possible when you use the rref?
Well, it depends on where you start with your question. If we start with a linear equation in the wild and ask how can we label the variables, the answer is there are many ways. And labeling the variables different ways corresponds to changing which column is which in the resulting system you look at. So if I take that freedom away from you, right, if you already give you the variables set with meanings, labels x1, x2, x3, xn, then we can ask your question again, which was what?
Which is, when you're doing your row operations, can you decide which variables become the pivot variables, or would you always get to the same pivot variables?
It depends on the system. Does x1 always have to be a pivot variable? No. How could x1 end up not being a pivot variable at all? What would have to happen is you'd have to have a system of equations where x1 just didn't appear in any of the equations, right? Which would make it a weird thing to look at, but maybe you're not looking at a single system of equations. Maybe you got two systems, right? One has x1 appearing in a non-trivial fashion, the other one doesn't, right? That could happen. So yes, it could happen that the first column is zeros, right? If the first column is zeros, then the second column would end up being the first pivot column, which would mean that actually x1 is a non-pivotal variable. That's a great question. Let me see if I can give you an example where that happens. I'll try to make it simple. So your example would be something like, I've got y plus z equal to 2, and y minus z is equal to, 3, whatever. And we're dealing with a xyz system. If I had that, my augmented coefficient matrix would be 0, 1, 1, 2, 0, 1, minus 1, 3, right? And how do I, well, okay, so I can't pivot on the first. There's nothing non-zero in the first column to pivot on, so I'm stuck. So my first pivot then would be this one. All right, and then so this is very boring. Row 2 minus row 1. I think we're done. So I really need to find some better examples for you guys. I mean, this is all your fault. It was your question. What was your name? Sam. This is all your fault. Sams are always troublemakers. Let's see here. See here. You happen to know Sam Shepard? No, okay. Let's see here. So, I guess we're not done. So why is this not reduced to echelon form yet?
Divide by 2.
Divide by 2, we could do that. But I'm going to do a different thing. I'm going to take this, I'm going to take row 1 minus 1/2 row 2, because we can do that, and I should show you that we can do that. Yeah.
2 minus row 1, so 2 in row 2 should be -2.
Did I write down the wrong thing? Did I not do what I said? It is 8:15, so if you see something, say something. I think I told you the guy said. Row 2 minus row 1. Oh, -2, thank you. So given that, instead of this, I don't want to do, if I do that, that doesn't accomplish what I want. Because my next goal here, guys, is to get rid of that. I want to make that 0. I want to make that 0. So to achieve that, I'm going to use this to zero that out. I want to put a half there. All right, so if I do that, 1/2 times row 2 gives me 0, 0, minus 1, minus a half. I add that to row 1. I get 0, 1, 0, 0, 0, minus 2. 1, what is 2 plus a half? 5 halves, okay, great. Almost done. So this is not yet reduced or echelon form, right? Because my pivot columns are not just the standard basis yet. So this is E1, right? But this right here is actually minus 2E2. So one more step, I need to take row 2 divided by minus 2 to get the reduced or echelon form, 1, 0. So you're like, well, do you have to get the reduced or echelon form? Well, that depends on the question. If the question asks you to calculate the reduced or echelon form, then I would suggest that you need to find it, yeah. But setting aside instructions, the question is, what are you after? What we're after is solving systems, right? So the nice thing about finding the reduced or echelon form of a system is it removes any doubt as to what the solution set is. Because once you get to the reduced or echelon form, you can write down the solution set. So this right here, what's this say? This says y is equal to 5 halves, and z is equal to minus 1/2. And x is free. X is free. What does that mean? What's the solution set then in this example? That's right, x is all real numbers. So the solution set, in this case, has the form x, y is 5 halves, and z is minus 1/2, such that, well, x is a real number. That's the solution set in this case. This is the geometric case I talked about last class, where we have, you know, we've got two planes, right? And they intersect along a line. And the coordinate of that line, it happens to be x. If you change x, you go along the line of intersection of these two planes, if you want to think about it that way. But we don't need to think about it that way because we have row reduction. All right. Let us look at another example. Oh, all right, so let me show you something before I don't want to hurry our next example. That would be bad, yeah. Why, let me put the zeros back into place for your question. What was your question again? I didn't quite hear.
Why do skips not together? There's non-zero numbers in there, but why is that not simplified?
But what do you mean simplify?
Well, so in the last example you gave, then it was like non-zero numbers.
Mm-hmm.
In the first one, so that one was kind of like skipped.
Yeah.
And then there's a stair step of one.
So,
Why do you just skip over?
so the thing is, the reduced or echelon form, every leading one, right? Every leading non-zero entry, if a row is non-zero, its leading entry has to be 1. If that is not the top row, everything above the leading one has to be 0, right? Everything below also has to be 0. which is another way of saying that the columns, the pivot columns have to be the standard basis listed in order. E1, then E2, then E3, all the way up to however many pivot columns you have. I happen to have 3 in this matrix. Yeah?
So for any system where you have more equations than you have unknowns, you're going to need at least one equation made of completely zeros, right?
If I have more equations than I have unknowns, I'm going to have at least one row of zeros. Correct. Yeah.
So you said that you can get a reduced row echelon form for any matrix. Can
That's
you
right.
do this for any matrix at all?
Yeah, let me show you. I'll let you guys make up the matrix this time. And we'll let the computer do the work. So I'm going to show you guys more examples. We ate up a lot of our time today just for me telling you what terms mean, you know. And I don't think we haven't done enough examples for this to completely set in. I get that, you know. I think you need to see about 4 or 5 examples before it really clicks. Because I haven't written out a step-by-step algorithm, right? I'm illustrating by example, which is always dangerous. But if you go to the course webpage, I will show you there is a website which will help us learn. This is such an amazing tool. I didn't have this when I was in your spot, but it is super nice. Oh, come on. All right, so here we are, Applied Linear Algebra course website. My number 4 matrix calculator site right here. This is a wonderful website made by a mathematician, which I won't try to say, Bogaki. I'm sure I'm saying that wrong. And so right here, this one, transforming a matrix to reduced row echelon form. Click on that. All right. And what do you guys want to do? What size matrix? Let's do what you said. More equations than unknowns. That means that I have like, you know, we'll do 4 rows and 3 unknowns. Well, I mean, I guess I better do. I'll get it eventually. Here, whatever. All right. So, oops. There you go. That's a system of equations. And so this actually shows you step by step what happens if you follow the standard Gauss-Jordan elimination, which, you know, identifies a pivot column, it clears out everything below the pivot position, and it systematically works until eventually, man, oof, ah, ouch. Yeah, I'm glad I didn't try to do this one. After this one takes 29 row operations, we eventually get to this. So if this is a system of equations, right? There'll be a vertical bar right here, right? So the original system corresponds to an equation in like x1, x2, x3, x4, right? What does this say? This says that after you reduce the system, you get to the equation 0x1 plus 0x2 plus 0x3 plus 0x4 equals to 1. That's a problem. That means that this system that I just made up, if we identify the original matrix as an augmented coefficient matrix, is inconsistent. So if you have a pivot column in the augmented coefficient matrix end up being the last column, you have an inconsistent system. But anyway, we need to do more examples next time. So I wish we had a 2-hour lecture for this particular topic. It'd be better, but it is what it is. Have a good day. Amen.